With sparse mixture of experts, you can grow the model's total capacity without using every parameter for every token. I'm Mehrdad. In this lesson, we will see how a router chooses a small set of experts for each token. Then we will look at why load balancing and communication determine whether that extra capacity helps in practice. Mixture of experts can look cheap because each token runs only part of the model. The active computation stays limited, so that computation cost looks fine. But with a real batch of requests, communication between experts can make the slowest requests much slower. That increase appears in P99 latency, which is the slowest 1% of requests. Active computation only counts the work the selected experts run, and it leaves out tokens moving between experts, so that network step still reaches the user as high-tail latency. Next, we will see what mixture of experts replaces inside a transformer block. Then we will examine the settings that control communication and P99 latency, not just active computation. If this series is useful, like and subscribe. First, let's place mixture of experts inside the transformer. In a dense transformer, every token goes through the same feed-forward network after attention. That network expands the token features, applies a gate, and brings them back to the model with. In a sparse mixture of experts model, this single network becomes a bank of feed-forward experts and a router. For each token, the router chooses a small number of experts. Only those experts run, and their outputs are combined. This lets the model add more total capacity without using the entire expert bank for every token. The rest of the transformer block keeps the same basic structure. Attention does not become the expert router. Attention assigns weights across tokens, while this router chooses feed-forward experts. So mixture of experts changes the feed-forward stage, not the whole architecture. Dense models are still common. Some newer models also use multi-head latent attention, but that is a separate serving choice. Now let's look at how the router makes that choice. For each token, a small linear layer gives every expert a raw score. The router keeps only the top K experts. In this example, it keeps the top 2. The selected experts receive gating weights, while every other expert receives 0. Each selected expert processes the token, and the model combines their outputs as a weighted sum. This is a hard routing decision because most experts are excluded. It is different from attention, which assigns soft weights across tokens. The router may use softmax when it calculates its weights, but the final choice is still sparse. In this lesson, each token chooses its experts. Another design lets experts choose tokens instead, but we will stay with tokens choosing experts. The router also needs a reason to spread tokens across the expert bank. At first, the load can look roughly even, with usable capacity across many experts. Without load balancing, traffic concentrates on a few hot experts while the others sit idle. The model keeps a large expert bank, but only a small part of it gets enough work to learn well. That wastes capacity. The busy experts keep improving because they see more tokens. The underused experts fall further behind because they see too few. This feedback loop is called routing collapse. In plain language, the router keeps choosing the experts that already look strongest and gives the others little chance to improve. We use load balancing so more experts stay useful and none get overloaded. The next step is to balance the load without damaging the model's main learning objective. A classic solution adds an auxiliary load balancing loss beside the main next token loss. The extra loss encourages the router to use experts more evenly. If its weight is too small, the load may remain uneven. If its weight is too large, it can pull learning away from the main language objective. Some modern recipes avoid that competition by adjusting the router scores directly. They measure how much work each expert receives and turn that measurement into a small bias. The bias lowers the scores of overloaded experts and raises the scores of underused experts. The router still prefers experts that fit the token, but it also responds to the current load. This method is called auxiliary loss-free load balancing, and it does not remove load balancing. It changes load balancing from a competing training loss into a score adjustment based on observed load. This is not a universal recipe, and Quen 3, for example, still uses a load balancing loss across the global batch with its fine-grained expert bank. When you compare mixture of expert systems, look at several settings together. Start with total capacity and the amount of computation that is active for each token. Then check the number of experts and how many the router selects. Also check whether the model uses shared experts and how experts are placed across accelerators. Finally, look at whether many tokens in the same batch prefer the same experts. More experts can add capacity, but they can also increase communication. Selecting more experts for each token increases active computation. Shared experts add work that every token must always pay for. You need several of these settings together, not one number alone. We will first compare total and active parameters. Then we will look at shared experts and the communication cost. Released models often list two different numbers for their parameters. Total parameters are the weights you must store and load. Active parameters estimate how much of the model runs for one token after routing. That active count is a useful guide to computation, but it is not a complete compute measurement. DeepSeek v3 lists 671 billion total and about 37 billion active. Llama 4 Maverick lists about 400 billion total and about 17 billion active. What runs for a token is not the same as what you must store. That same gap matters later when you compress the model. Lower precision still has to shrink the full stored weights, even though only a smaller active path runs for each token. Some mixture of experts designs add shared experts. Every token goes through an always-on shared compute path, while the router also selects experts from a larger bank. These two paths run in parallel, and the model combines their outputs. The shared path always runs, so every token pays that compute cost. The routed experts are selected per token, and any specialization comes from training statistics. It does not mean one expert has a fixed label such as code or mathematics. Shared experts are common in modern designs, but they are not required. Llama 4 uses shared experts with a very sparse top 1 routed choice. It also alternates dense layers with mixture of experts layers. QN3 uses fine-grained expert banks without shared experts. These are different design choices, so do not treat one model architecture as the rule for every mixture of expert system. Now, we can explain the slow requests from the start of the lesson. Large expert banks are often spread across several accelerators. This placement is called expert parallelism. A token may need to move across the network to reach its selected experts. Many tokens moving between devices creates an all-to-all communication step. With a real batch, that exchange can dominate the slowest requests even when active computation remains modest. Network movement can set tail latency. Active computation measures only part of the serving path, so it does not predict end-to-end latency by itself. How training tries to hide that communication behind other work belongs later in the series. A mixture of expert system has 3 different costs to track. How much memory you need depends mainly on the total parameters. Computation per token depends mainly on the active path. Communication depends on expert placement and on how tokens in a batch are routed. More total capacity does not guarantee better quality or lower latency. Spending more active computation makes sense when limited computation is holding quality back. Sparse mixture of experts is useful when you need more model capacity for the active computation you spend. It is less attractive when network communication or simple response time is the main constraint. Dense models remain a strong choice when simpler deployment or a smaller stored model matters more. Lowering precision can shrink the stored expert bank, but it does not erase interconnect cost or change which experts the router picks. Measure the bottleneck in your own system, adjust the design, and measure again. A larger total parameter count is not automatically better for serving. Let's close with 3 ideas. First, mixture of experts replaces the feed-forward stage with a routed expert bank. Second, load balancing and communication decide whether that extra capacity helps. Active computation alone does not tell you the P99 latency. Third, read total and active parameters separately. Shared experts and load balancing methods are design choices, not one universal recipe. Next, Video 7 will compare usable context with the context length listed for a model. I'm Merdad. Thanks for watching. Like and subscribe for the rest of Transformers and large language models, and I'll see you in the next lesson.